Hello students, today we are in lecture number 13 of chapter 1, Electrostatics. Student, as I told you in last lecture, we'll discuss today about the flux, electric flux, which is important for the Gauss law. To study that electric flux and Gauss law, to understand the Gauss law, we need to know first about the solid angle. It is a physical quantity, solid angle. If you recall, we can represent by ohm or omega. If you will recall the 7 fundamental quantity and 3 supplementary quantity, you will find the solid angle was the one of the supplementary physical quantity whose SI unit we have been taken as a steradian. Okay, student, that solid angle we are going to talk about. Solid angle actually, student, it gives the space or area. Okay, student, the space or area enclosed around any point. Enclosed around any point. If this is the point, so this enclosed the area, a specific area. If we talk about this area, okay, this is enclosed, this one, this much area. So this space is basically called solid angle. We are representing by ohm. Try to understand this by another example, student. But remember, this is nothing but the space or area around a point. Which is enclosed by the specific surface. Solid angle enclosed by specific, or you can write here, enclosed by surface area. Surface area. Okay, within the point. I'm trying to explain you, okay, student, about this solid angle. Otherwise, the maximum students confused about this solid angle. Suppose this is a sphere. If you reach to the market to buy watermelon, you will see that person who is selling this watermelon trying to check whether that is red or not, whether that is in well condition or not to sell. He used to cut in a spatial shape, okay, in this way. This is the spatial shape he used to cut this watermelon in this way. Okay, if you will take this piece out from here, you will find the shape in this way, and this portion actually, this goes to this point, this portion actually cut out from here, this watermelon section. The section will give you this particular opening, will give you the solid angle, and this actually surface area is giving you the solid angle. This surface area can be represented by the elemental representation. It is ds. Okay, this is the elemental surface area. Around this point actually we are obtaining here the solid angle, this one, omega, okay, or the ohm. At this specific length, this area matters, how much this area or the space will be. At this specific length, this area matters what will be the solid angle. Otherwise, if you will change this length, this area might be changed for the same solid angle. For example, here, if we will draw from the sphere, and this is your surface area, okay, at this point the solid angle, for this solid angle omega 1 or the ohm 1, the area is ds, okay, the surface area vector. For this solid angle again, which is omega or ohm 2, the area is similar. Remember, this ohm 1 and ohm 2 are both equal. Remember, both are not different. The value will be same. Now, what will be the solid angle, the total solid angle around this point maximum value? What will the maximum solid angle, student, you can consider about this one? The plane angle is something different, and that is very easy to understand, student. The plane angle you can make by joining two lines. This way, this will give you the plane angle 30 degree, whatever, theta degree. But is the solid angle is the space. For example, suppose you are having a paper and you make a cone with the help of this paper. As a cone, this cone you use to eat. So thus a space, you can find that space is the solid angle. Okay, if you will increase this area like this one, if I am just opening this one, you have been increased, so that solid angle will change. Here about this point we are making, about this point of the cone, about this point we are making the solid angle, we are studying the solid angle. So what will be the maximum angle about this point? So the maximum angle are the number of cones you will form to make, and this will be the complete about to just hide this point. You need to make a sphere. Okay, the sphere only enclose that point completely, and then you will have the solid angle in this way, student. Okay, if this is the sphere, okay, this is the sphere, then you can write for the total area, surface area of the sphere will be how much? It is 4, if the radius is r, then 4 pi r square. For this complete surface area, we know that the solid angle will be 4 pi. You have to remember, okay, it is 4 pi. For specific surface area, what will be the solid angle we are going to find out? For specific area, the surface area, what will be the solid angle? The maximum will be, it is 4 pi. You can also prove that the maximum solid angle will be 4 pi. For unit area, how much it will be? 4 pi over 4 pi r square, and for unit surface area this one, and for surface area ds, this will be 4 pi by 4 pi r square times ds, and this is nothing but the solid angle for elemental area ds. It will be cancelled out, so it is ds by r square. Now this solid angle we will treat as positive, okay, as a vector quantity. We will treat this as a vector quantity. And in what way we can represent this as a vector quantity? If this sphere, here the surface area, it is ds, surface area must be perpendicular, so this direction ds, remember, must be perpendicular to the surface, and if it is perpendicular to the surface, then direction will be along r cap, because at each point the surface perpendicular direction will be radially outward. Okay, so the radial vector will give you the direction, and then this solid angle d ohm can be written as the ds over r square dot r cap, or you can also write this way, this d ohm as d ohm as ds dot r. It is the two vector quantities, and this is also vector quantity, and this is the vector quantity. So the cosine of angle between them, ds cos theta by r square. And this r is nothing but, remember, this r is nothing but the radius of this sphere we have been taken. So you have to remember this formula, that is the solid angle, elemental solid angle will be equals ds cos theta by r square. This the same derivation or the same concept you will use to verify the Gauss law. Okay student, now we are going to study about the electric flux. What is electric flux? Okay student, actually electric flux, to study electric flux, because we have to study the magnetic flux also, this meaning of flux need to be known. Flux, literary meaning of this flux student, it is to flow. Okay, to flow, the flow of water, the flow of air, flow of electric field lines, flow of magnetic field lines, that all will be considered as the flux. Okay, so the electric flux, if we talk about the electric flux, then we are talking about the flow of electric field lines. Flow of electric field lines, and that flow of electric field lines, it means you are willing to find the number of field lines actually from any particular surface area. Suppose I have been placed a ring over here, and these all are the, remember, imaginary, because electric field lines you cannot count. If we are looking at the 1 2 3 4 electric field lines are crossing this particular ring. Okay, this is the ring, and the number of field lines are 4. So we are able to count this number of field lines, and this counting will give you the electric flux. So we can write here the flux, if this electric flux represented by phi. Okay, for electricity we'll use phi E, and for magnetic phi B. So the electric flux is nothing but the counting here, the 1 2 3 4. Okay, so the counting of field lines will give you the electric flux. It is the counting of field lines from any cross-sectional area. Okay, from any cross-sectional area. It is the counting, nothing else. This is the counting of electric field lines from any cross-sectional area. Total field lines, if you will write the definition of this electric flux, proper definition, then you can write it is the total electric field lines flowing through a given cross-sectional area is called electric flux. This is the definition I have given you of the electric flux, student. Now student, how will you count the maximum? How you will count the total, that is the maximum field lines passing through any cross-sectional area. Suppose this is the plate, and this plate you have been placed to stop the field lines. which is going from here. Okay, this is the surface area. You can write the area vector also. This is the area vector. Here you are capable to stop the maximum. Okay, here you are capable to stop the maximum filled lines. You can see, if you will tilt the plate, if you will tilt this plate, the plate is this one, and the filled lines are coming in this way. Okay, this in this way. If you will tilt this plate in this way or in this way, the filled lines will go from above, or if you will tilt this way, the filled lines will go from down. So in this way, this plate has the capability to stop maximum as per its own, okay, potential or the capacity. But if the filled lines are flowing in from this way and you have been tilt this plate in this way, so try to understand how many filled lines you will be able to stop, or how many filled lines this plate will be capable to stop. Actually, the maximum filled lines will move without stopping, okay, without stopping. So the flux will be almost very negligible and totally depends upon the thickness of the plate. If this thickness is very small, then the flux will be how much? Almost zero. So if the fill lines is coming from this direction, if fill lines is coming from this direction, so the plate will be able to just stop the maximum fill lines. That is, it will count the maximum fill lines in this way. So this will give you the maximum flux and this will give you the minimum flux. Okay, so often we will use this minimum flux as 0. But it is quite obvious, rotating the plate in electric field, the counting will change. That is, the electric flux will change. Here, suppose plate is oriented in such a way, this is the electric field, and plate is oriented in this way. This is a circular plate and electric field in this way, but plate is oriented in this way. Okay, area is in this direction. It is making an angle theta. So whether in this orientation this plate will have the maximum counting, the answer is no, this will not have the maximum counting. In which direction it will have the maximum counting? So it need to be tilted in this way. As you will tilt this plate in this way, so the area will go along the electric field, and along the electric field the area will have it is component of this area vector A cos theta. Okay, student, now we'll try to understand the mathematical definition of this electric flux. Actually, mathematically, this electric flux is defined as, mathematically it is defined as the product of this electric field and area vector. Okay, and we have to generalize this definition so that we can use this definition for any angle. Okay, so this electric flux is nothing but the product of electric field and area along the direction of field. If you write, this flux will be in this way: E A cos theta. This E A cos theta can be also written as, students, as the mathematical vector product as E dot A. Okay, E dot A. Student, you can write here the A dot E also. Okay, there will be no change in meaning, E dot A or A dot E. So in a few books you will find the definition as the electric flux is defined as the dot product of electric field and area vector. Again, it is defined as the dot product of electric field and area vector. Okay, student, now we'll focus over the SI unit of this electric flux. Since, my dear students, this electric flux is counting, then of course it will be the scalar quantity. Okay, it is a scalar. Now the SI unit. Since this is EA, phi is E, and the SI unit of E we have studied already. The SI unit of E as Newton meter square. Newton meter square per coulomb. This Newton per coulomb will be E. That is the force per unit charge, Newton per coulomb, and this A will give you the meter square. So this will be the SI unit of this electric flux. If you can write, then try to write by yourself the dimension of electric flux. Okay, now we are going to generalize over here the electric flux for its maximum value and minimum value. Okay, so this will be the special case. I hope that you are in position to give the answer, whether the flux is maximum, whether the flux is 0, okay, and whatever may be. So you can write the flux. This is the plate area, and electric field is coming from downward. If this is the plate area A, and this is the electric field, what will be the theta over here? Theta is how much? 0 degree. Then the flux will be E A cosine 0, and this flux will be E times A. Of course, this plate is capable to stop maximum flux. Okay, now here in this way, and electric field is going in this way. Okay, this is the electric field and the area vector over here. Here the angle between area vector and electric field is how much? Theta is 90 degree. What will be the flux? Here the flux will be E A cosine 90 and cosine 90 0. So the flux will be how much? 0. So this plate, we are neglecting the thickness. So here the counting of field lines will be 0. This plate is not capable to stop electric field lines. Then what will happen if we'll study this area vector from downward? Okay, from downward. This will be in this way. Area vector downward. If you turn the plate, here the theta, how much? Again, the theta is 180 degree with the electric field. So phi will be E A cosine 180 degree, and thus phi is minus EA. Now, sir, if this is scalar quantity, then what is the meaning of this negative of EA? Actually, my dear students, this is the 0, okay, not confusing, but this electric flux, we can see it is leaving the electric flux, actually counting electric flux, we are counting from outside, okay, from outside the surface area, this one, and electric field is coming toward us if we are outside. If the surface area is over, then we are starting the flux from outside. Suppose if you are sitting inside the room and this is the wall of your room, then you must be able to see this wall, not the wall behind this one, and the area vector will be in this way, and the electric field is coming from downward, then of course the electric field is coming towards you, that is parallel to the area vector. So this one is the case. Okay, you are outside, the plate area and you are looking that flux is coming out. That's why this is called the outward flux. Outward flux. Whenever you will get the flux, it is the angle between area vector and electric field, it is 0, then you will write this is as outward flux and this is as inward flux. This is as inward flux. Inward flux. Okay, now the very interesting thing, my dear student, if I'll place a cube, okay, if I will place a cube, this cube, and it is immersed into the electric field. Of course, the area of each plate is equal. Now try to find out which plates are not capable to stop or which are not capable to count the electric field lines. It is this area, 1, the bottom one, okay, the bottom one, this bottom one, this is not capable to count the field lines, this is also not capable to count the field lines, okay. Now this front one, okay, this front one is also not capable to count because the area vector will be outward and the electric field is going in this way. So the electric field and area will give you the 90 degree, and the behind this one, okay, just below this top face, that face will also make 90 degree with the electric field, so that will also not count. So the total phases those are counting this electric field lines is this one, if this is the x-axis, so this one which is having the area vector a minus I cap, and this one which one having the area vector I cap, okay. So these two will count the field lines. Now the question is, what will be the total flux, net flux? It is very simple. If you will count the net flux, here the flux is going and this way, it is inward flux, this one, area vector and electric field making 180 degree. So this is inward flux, and from this face this will be the outward flux, since only these two phases are counting the field lines. So the total flux will be, the total counting will be same, okay. So this is counting phi as positive, this or the negative if you are counting this as inward, okay. Let us this one as positive and this one as negative, but we have been written here negative, no? So the minus phi and this one as plus phi. How much it is? 0. Interesting result, and this is the important result. You have to remember, if any closed body completely immersed into electric field, then it will count total field lines as 0. Why? Because the number of field lines that will enter into the body, the same electric field line have to leave the body if it is closed. Then whatever may be the shape or size of the body, if it is completely immersed into the field lines, then it will have the zero net flux, zero net counting. Remember, whatever may be the shape and size. So a closed body will have net flux 0 if it is completely immersed into the electric field. Okay, my dear students, so This will be your note point, and on the basis of this note point we will solve number of questions that may be asked in competition. So this is all about today lecture, students. Thank you very much.